Okay, so chapter 1, the science of psychology. And yes, I am Dr. Freddy Aviles. Okay, I am your instructor for the course. So what is this first chapter about? Well, the first thing we start off with over here, the question there is, why take a research methods course? Why would you want to take a course like this? I know what your answer is. It's because you have to, in order, to get the psych degree, the psych transfer degree, and that's probably your answer. But there are actually other reasons why you should take this course. First thing listed there, it says, to learn how to apply science to the study of human behavior. Okay, yes, basically, we're going to learn about the scientific method. Okay, to learn how to do science, to learn how real research is done. You guys are going to do that in this class. You're going to do your own research project, okay? And you're going to actually apply the scientific method to understand and interpret others' research. You might have done papers for other classes like Psych 101 or any other psychology class, or maybe even another type of class that's not psychology, where you actually had to read research articles. And you read about methodology. You read and tried to understand these statistics that are mentioned there. And you probably found it somewhat difficult. There's a lot of things there that you may not understand. After taking this class, you will be a lot better at understanding those research reports, understanding the methods, understanding the statistics. There'll be some that you'll understand perfectly well, and there'll be some that you still won't understand that well, because we're not going to talk about every single method. We're not going to talk about every statistical analysis. So there will still be some things you may not be too clear about, but you'll be a lot better at it, okay? And then, of course, if you go on to graduate school, then you'll learn even more, and it'll be even easier for you guys to understand that stuff, because you'll be doing your own research. But this is an introduction. You're not going to learn everything. To evaluate claims in everyday media. A lot of things are presented in the media as if they are fact, and some of those things are actually ridiculous. The people who are presenting these claims in the media are not research scientists. They don't understand that the results need to be, reported in a certain way, or that you can't claim cause and effect when a study, for instance, was done using a survey. So they'll, they might report something, study finds that the type of potato chip you eat, actually says what kind of personality you have. What the study probably found is that there's probably a correlation maybe between your personality and the type of potato chip you eat, but we don't know if that was done correctly. There may not be such a correlation, and you should never claim from a survey that the actual potato chip has actually anything to do with your personality, anything to do with the cause and effect, okay? Or study finds that eating broccoli can prolong your life. No, broccoli is not gonna make you live longer. That study was probably done using a survey, and what the study probably showed is that people who have healthy eating habits, they eat healthy, but broccoli by itself people who have healthy eating habits live longer. Okay, but it was still, done probably doing some kind of survey or something like that, or at least people live until, a ripe old age if they eat healthy. They try to claim that the broccoli is what's making them live longer, when in reality, that's just the one little piece of it. Okay, anyway, yeah, there are claims like that. If you know how research is done, you can probably spot the ridiculous claims from the ones that probably are more credible, okay? To discover how to acquire and make decisions by applying the scientific method. Yes, that has to do also with the first thing listed there. You will learn to apply the scientific method, how to actually do research, a little mini research project. And, it's a very valuable thing to know how to do. Okay, move on. I probably spent way too much time on that slide. Let's move on. All right, now let's talk about methods of knowing and acquiring knowledge. Okay, methods of knowing and acquiring knowledge. So how do we know anything? Okay, there are both non-scientific methods to acquiring knowledge, and then there's a scientific method, okay, which of course is scientific. The very name is in there. So here are the non-scientific methods: the method of tenacity, method of intuition, method of authority, the rational method, and the method of empiricism, or we can just call that empiricism. And then there's the scientific method, which actually makes use of some of those approaches and then adds to them. So let's talk about these approaches. The method of tenacity. What is tenacity? Okay, when you're using the method of tenacity, the information is accepted as being true because it has always been believed or because of superstition. In other words, you've heard something over and over again and you assume it's true. You've probably heard the expression opposites attract, right? We've heard that so many times. At least I did when I was growing up. I don't know how often you guys hear it now. I mean, we're living in a different age now, a digital age. But you've heard that a lot, okay? And some people may believe, yes, that, you know, it's true that opposites attract. In other words, you know, that nice, good girl can hook up with that bad boy and somehow things are gonna work out and they're, you know, they're gonna be attracted to each other and it'll be a successful relationship. I can tell you now that research does not support that. No, opposites do not attract, okay? It works with magnets. It usually does not work with people. People who are opposites usually don't like each other. They often hate each other, okay? It doesn't work. And if you marry someone who's very different than you and believes very different things from you, you're likely not gonna get along and you're probably more likely to get divorced, okay? You've heard the opposite expression, birds of a feather flock together, okay? That one is supported more by research. Yes, people who are more similar are better suited for each other, you know, for being friends and romantic partners and marriage partners and things like that, okay? But no, opposites really do not attract, not when it comes to relationships usually, and that's what that is saying, opposites attract. Or you might have heard, you know, things like, you know, like if you have maybe a lucky shirt or some lucky socks or lucky hat or something, that things will go well for you. Like, you know, if you believe that if you wear your lucky socks, you know, you're going to play well. Let's say you're an athlete or something like that. That's just superstition. People mistakenly believe, for instance, that their lucky socks have something to do with them playing well. And there's no such connection. Okay. It is just coincidence. Okay. So when we're talking about something that has been said over and over again, or something that you believe because of superstition, you know, that is the method of tenacity. You believe something because you've heard it a lot or because it's just superstitious behavior. It's just superstitious beliefs, okay? It's not scientific at all. So limitations, potential inaccuracies. Yes, often those things that you've heard over and over again, they will be wrong sometimes, okay? There is no way for also correcting erroneous ideas. You actually ignore contradictory evidence. If you believe opposites attract, then when they don't, you know, you're kind of gonna ignore that and you're gonna pay attention to the time, you know, the times when, you know, it does work, when most of the time it actually does not work, okay? Or wearing your lucky socks. Let's say you wear your lucky socks and you play well and you wear your lucky socks again and this time you play awful. You're gonna kind of discount or ignore the times when it didn't work for you and still tend to believe that your lucky socks actually do make you play well. So there's nothing scientific about this. You're not using the scientific method. So, you know, that's one approach to acquiring knowledge and it's not a very good one. Let's keep going because I'm talking too much. Okay. And there's also the method of intuition. We've all heard of intuition, right? When you have your gut feeling, right? Something tells me that I should bet on number 23, right? Or something tells me I shouldn't trust this guy or this girl or something like that. That's your intuition. You have kind of a hunch or a gut feeling. Your intuition is actually very useful. It's kind of like, you know, some people have called it like another sense that tells you something, but you don't know where that information is coming from. Like something tells you that you shouldn't trust this guy, okay? You don't know why. You have no evidence, you know, to support your, you know, to support the idea that this person can't be trusted. But you have this gut feeling, you have this hunch. There's probably something biological there. There's probably something evolutionary that we've kind of have, you know, like when you meet someone and the hair stand up in the back of your neck telling you like, this person's probably dangerous, you know, something like that. Science has studied intuition, you know, a bit, and some have suggested that your intuition probably does have something to do with your biology, that on some level you may be acquiring information that is maybe unconscious, and and that's why you have this intuition. You have no idea that you have this information. It feels like it's just coming out of nowhere, but there is something there. Like, for instance, let's say you walk into a bathroom and you hear nothing, you see nothing, but you have this creepy feeling that somebody is in there. Okay? What's going on? Some research suggests that you may actually be detecting some sound, some odor, maybe at such a low level, but you're not conscious of it. You're not aware of it. So it just seems like you just have this feeling for no reason. But there actually may be a reason for it. It just may operate at an unconscious level. That's your intuition. It has its limitations. It's not a perfect method for acquiring knowledge. There's no method for separating accurate from inaccurate knowledge. Again, you're not using the scientific method, okay? You're not really using any science here. It's just your gut feeling. And your gut feeling can sometimes be right. It can sometimes be wrong, okay? But you're not really testing it, okay? Let's move on. That's your intuition. The method of authority. This one's very popular, okay? A method of authority. You can probably guess what this one's about. The method of authority. It relies on information or answers from an expert in the field. So if you want to know something, you can just ask someone who is an expert, someone who's an authority. Let's say you have a certain, legal problem and you don't know what to do. Well, if you know a lawyer, ask a lawyer and they can probably give you some answers. Or you want to know, is there a God? Well, what do you do? Maybe you ask a priest, a pastor, someone like that. It's a way of acquiring knowledge where you just rely on these so-called experts. It's a good starting point. It's often the quickest and easiest way to obtain answers, okay? Or let's say you want to know, like if drinking alcohol is actually bad for you or if it's good for you. Sure, you've heard about both things. So maybe you might want to ask an expert, someone who actually studies alcohol for a living, a scientist. Okay, so it's a good way to actually obtain answers, a very quick way, but it has some problems. These experts don't always provide accurate responses, accurate answers. Sometimes these experts are wrong. They don't know everything, and often they don't want to admit to you that they don't know, and they'll make something up. And sometimes these experts' statements are accepted as, just being fact, like the method of faith. It's just, it's true, your pastor or priest or something says that God exists. It's just that, right? That's the method of faith. You just have to believe it. And I think I might be getting ahead of myself here, but as you guys might be aware, a lot of so-called experts aren't really experts. There are people who actually fake being an expert, okay? There are fake lawyers and people who are fake doctors and who basically just want to, tell you something, and get you to give them some money and then disappear on you, okay? And there's a lot of people out there who are just popular and well-known. And, sometimes people want their opinion. What do you think about gay marriage? Or what do you think about Trump or this? Just because they're popular doesn't mean they know what they're talking about. Or just because they've been elected to office, by the way, okay? Just because so-and-so is elected doesn't mean that so-and-so knows what the heck he's talking about when it comes to, let's say, the environment, or when it comes to health, or, or whatever it is, They are people who have been elected because they're popular, because they're well-known, and people like them. Sometimes they're really smart and know what they're talking about, and sometimes they're not. And that's the problem with relying on experts, okay? Although I will tell you that science does use the method of authority a little bit. It actually does make use of it, because when you write a research report and you write that introductory section, what are you doing? You are actually talking about other people's research. Those are experts, those are people you're relying on to then derive your own kind of hypothesis, your own rationale for doing the study. So the method of authority can be useful. Just be aware that not everybody's an expert. Not everyone should be believed. And that's why you need to know about the scientific method. That's why you need to know how to accurately evaluate claims, okay? Whether they come from the media or from a so-called expert or a book or whatever it is, okay? Let's keep going. There's also the rational method. The rational method. The rational method just uses logic. It uses reasoning, okay? So in other words, it tries to derive an answer kind of in a logical step-by-step manner. There's an example here. There's your premise there, right? You assume that something is true, and then from there you derive an answer. So the premise there says that all 3-year-old children are afraid of the dark. Okay, that's your assumption. And then Amy is a 3-year-old girl. Therefore, Amy must be afraid of the dark. If all 3-year-old children are afraid of the dark, and Amy is 3 years old, therefore Amy is afraid of the dark. That is logical reasoning, okay? That's what that is. It makes sense, but it's not a perfect method for acquiring knowledge. Because let me explain a little bit more. In the above argument, it says the first 2 sentences are premise statements. These are assumptions, things you assume to be true. And often that's where the problem starts. Sometimes your assumptions are wrong, and then what you logically deduce is not valid. The final sentence is the logical conclusion, the logical outcome of those premises, of those assumptions. Like for instance, I can make a logical argument, okay? Somebody has been messing with my sprinklers. That's I know that to be true because I've seen that, okay? I've been out there and I've seen that. And then there's the other assumption. My neighbor doesn't like me. That's the other assumption, okay? And then my logical argument could be, well, my neighbor's the one messing with my sprinklers. And that might be wrong, and it might be right. I've actually used logic there, and it makes sense. But actually, in my case, believe it or not, I was wrong. It wasn't my neighbor who was messing with my sprinklers. It was raccoons. But logically, it made sense for me to think that. But you see how logic doesn't always work? Let's move on. There's more about logic here. Limitations to the rational method. Limitations to using logic. Logical conclusions are only valid if the premise statements are true. If your assumptions are true, okay, then your conclusion might be valid. But even then, it could still be wrong, okay? But it's valid that you derive that, okay? But it may be wrong. And the thing is that people are actually not very good at logical reasoning. Everyone thinks they know how to use logic, they know how to produce these logical arguments, and they don't. Most people aren't very good at this. Take a class on logic. It's a philosophy class. And learn how to use it better, I guess. But everyone uses logic at some point. People have their reasons for saying that Trump is a horrible president, or they have their reasons for saying he's a good president, and they try to use logic. Because of this and this, therefore Trump is awful. Or because of this or this, therefore Trump is great. You can make an argument for anything, and you can use logic, but how good are you at it, okay? And research shows that most people are just not that good at it, okay? And even when you use logic correctly, you can still be wrong. I mean, people looked up at the moon a long time ago, and they say, look, it appears to be a certain way. Well, actually, I'm getting ahead of myself. Forget the example about the moon, okay? It's gonna confuse you guys, all right? I think it has more to do with the next method. I'm getting ahead of myself. Okay, so that's the logical method or the rational method. It's called the rational method. There's also the empirical method. Now, the empirical method is a little bit better. It's also known as empiricism, answering questions by direct observation or personal experience, okay? So this is where my example was heading. I was getting ahead of myself. The empirical method. So you derive knowledge by using your senses. That's what this method is, okay? You observe, okay, in other words, okay? The empirical method is based on the philosophy, it says there, that all knowledge is acquired through the senses, okay? All knowledge is acquired through the senses. That's a, an assumption there, actually, okay? So if we see something, if we hear it, if we smell it, if we can touch it, that means it exists, okay? That's the empirical method. It sounds okay, right? It's actually something that is part of the scientific method. It does use empiricism. It does rely somewhat on the senses, but that's not the only thing the scientific method relies on. But using your senses, using the empirical method has some limitations, okay? First of all, observations can be misinterpreted. what you see may be wrong. It may be an illusion. Your sensory experience can actually be swayed by your beliefs. You can actually think you see and hear something because of what you believe. Let's say you believe in ghosts. Well, guess what? You hear some funny sound or some weird sound, or you see something in a flash, you know, you didn't really get to see it very well. You might think it's a ghost. I've seen, I've talked to people who have had those experiences, and I've talked to them, and yeah, you know, it was because of what they believed, that they were seeing a ghost or hearing a ghost or something like that. Your beliefs can alter what you actually perceive, what you actually, you know, see and hear and all that stuff. Or you just interpret those things as being, you know, evidence for the fact that there's ghosts or something like that. Also, we're talking here about the empirical method, just so you keep track of it. The empirical method is time consuming. Okay, it can take a long time to actually find out for yourself. Okay, let's say we want to find out if there's life on Mars. All right, well, you know, we have to send that rover over there, or maybe we want to send people to Mars, and so we can see for ourselves, right? Or maybe distant planets that, you know, we can't even send any rovers to, you know, because it'll take, you know, hundreds or thousands of years to get there. Okay. It can be time consuming to acquire knowledge that way, or to find out for yourself. You need to see it to believe it. Okay. And sometimes it's dangerous, right? We want to send people to Mars, find out if there's life there. It's going to be dangerous. People are probably going to die. Just like, you know, when people try to find out what's in our oceans or what's in that island far away, you know, those travelers, those navigators that were trying to explore another land, finding out for yourself, you know, through your own senses is useful, but it can be dangerous and time consuming. Okay. And here's an example of how your senses might not be telling you what you think they're telling you. The horizontal vertical illusion. Believe it or not, those two lines there, the vertical line and the horizontal line, are actually the same length. I know you think that the horizontal one is probably shorter, but if you actually measure them and then you put them right next to each other, you'll see they're the same length. But here's an example of how your senses are so easily fooled. And there's a lot of other examples. Your hearing can be fooled. You know, even your sense of smell. There is the, you know, the contrast effect, right? When, if you put your hand in a bucket of like really hot water, and then you put your hand in a bucket of lukewarm water, you know, if you do that, if you put your hand in a bucket of really hot water, and then you put it in a bucket of, let's say, tap water, or no, lukewarm water, the lukewarm water will actually feel cold because of the contrast effect. Your senses can be fooled. They're not perfect, okay? The mind has a way of being fooled, okay? And there are naturally occurring illusions out there. Okay, let's keep going. Well, here's a summary. We just talked about this, so I'm just pointing it out, right? These are the 9 scientific methods of acquiring knowledge. Tenacity, you know, just because you've heard something over and over again, or superstition. Intuitions, just you have a hunch, a gut feeling. Authority, an expert tells you something and you believe it. That's, you know, that's knowledge you assume, right? Or rationalism, or you know, or basically using reason, using logic, the rational method. You use reason, logic to arrive at a conclusion, and your conclusion may be wrong. And empiricism, from direct sensory observation, right? You believe something because you've seen it for yourself, you've heard it, tasted it, you touched it, you smelled it. Your senses can be fooled. So these are all non-scientific, okay? But let's talk about a scientific method of acquiring knowledge. That is the scientific method, okay? That's what it's called. It's a scientific method, okay? It's an approach to acquiring knowledge that involves formulating questions and then systematically finding answers. So we'll go through the steps in a moment, but you want to know something, you have some question, and you want to find out what the answer is. This scientific method actually combines several methods of acquiring knowledge. Believe it or not, it makes use of some of those non-scientific approaches. I can tell you, looking back over here, that it will use, you know, rationalism. It will use the rational method. When you derive a hypothesis, for instance, you know, you have a statement, right? You know, if this, then that, okay? If participants consume alcohol, then they'll act more aggressively. If they don't consume alcohol, then they won't behave aggressively. That's logic, that's reasoning, right? That's the rational method. You're making use of that. It also uses empiricism. It does rely on sensory observation. You actually test things. Maybe you actually do an observation, right? Where all you do is, you know, look at something and you report it. Or, you test people's sense of smell or taste, or, you see something with your own eyes. So it makes use of those too. Oh, and I almost forgot, it also makes use of the method of authority, because you actually read about other people's research, other people's experiments, other people's, studies. And then from there, you try to, logically derive, let's say, a good reason for doing your study, okay? So it actually makes use of those last three. It doesn't really rely on tenacity or intuition so much, although those things can be tested themselves, but they're not part of the scientific method. But the scientific method does more than that, okay? So let's keep going. So here are the steps to the scientific method. Now, these steps are going to be more detailed than what you've learned, let's say, in a, in a 101 class or another introductory class. But this should sound familiar. So the first step of the scientific method, and I want to point out also that the way the scientific method is presented can vary from class to class, okay? The steps are actually the same, except that, sometimes they start with, let's say, instead of an observation, they might say, well, maybe you have a question, okay? Or there's 5 steps rather than 6 steps because they've combined some, or maybe it's presented as 4 steps, but it's really the same thing. What you guys have to know for this class is the scientific method as is presented here. So the first step is to observe behavior or other phenomena, okay? So usually scientific method starts with an observation. You notice something, okay? You're outside walking around and you notice something. Or maybe you're watching TV and you notice something, or you're reading a book. These observations can come from anything, anywhere, okay? So it could be a casual observation. You're walking around, you see something, right? Or others' observations. You're reading a book and somebody mentioned something and you wonder if that's true, okay? Inductive reasoning, okay? Inductive reasons, okay? So maybe you logically derive something, right? From other assumptions you may have. And that's your observation, right? So I'll give you an example of deriving, of inductive reasoning, actually, observing something through inductive reasoning, okay? The first step there. So an example of inductive reasoning. I know it's kind of lengthy, okay? But you can see there, it says, an example of inductive reasoning. You notice that it is cold, dark, and dreary, right? We wish it was cold. Right now, it's super hot. But you notice, let's say that it is cold, it's dark, it's dreary, okay? And you also notice that you're feeling a bit down. You notice your friends also are feeling a bit down. They're not doing too great either. So from those observations, right, from those things, you basically reach the conclusion that maybe people are sadder, if that is a word, right, or more sad, I think is more correct to say, right? Maybe people are more sad during winter than in the summer. And you guys know about this already. There is such a thing. It's called, seasonal affective disorder. That's what it's called. But you might derive this observation on your own just by things that you notice. And that is the first step. You observe something, or you derive something from other observations. Okay, so that's the first step. Observe behavior or some other phenomena. Okay, so observation. Okay, and here's the thing. Oh, you know what? When I view things on the iPad, it doesn't, sometimes it doesn't present things as, that well. It moves things around a little bit, as you can see by some of my bullets there. And here it cut out the number 2. Okay, so the second step, when you guys download it yourself, you'll see it clearly, and you'll see the number 2 there. Okay, it's not missing. So the second step here of the scientific method is to form a tentative answer or explanation. You guys have heard about this, right? A hypothesis. Number 2 is to form some kind of hypothesis. So you guys might have heard from other classes that, or even from high school, that a hypothesis is an educated guess, right? It's like an answer to your question. It's a guess. A hypothesis is a little bit more than that, but that's one way to put it, okay? So hypothesis, right? It's an answer to your question. right? There's something you observed, okay? And you notice something, okay? And then you try to explain it, No, wait, you come up with a hypothesis, an answer to that thing that that question that you have based on an observation, okay? So I'm getting ahead of myself here, but this will come up again, all right? For your hypothesis, you have to identify the factors or the variables associated with your observation, okay? Variables, to put it simply, are just things that vary, okay? They are characteristics or conditions that change or have different values for different individuals. The weather can vary, the economy, the health, somebody's, opinions can vary, laughter can vary, number of pets you have or whatever it is, whether you're married or not, lots of things can vary. Those are called variables. So your hypothesis basically, has to some extent some variables pointed out, okay? So here's an example of a hypothesis here, okay? It says people become depressed in winter because the weather is dark and depressing. That's the hypothesis, right? That's your kind of answer. You wondered if maybe the weather has something to do with how people feel. And your hypothesis or your guess, your answer to that is, yes, it does. People become depressed in winter because the weather is dark and depressing, okay? So there's some variables there. The weather varies, people's depression can vary, okay? So I'm getting ahead of myself. Believe it or not, we're gonna have a chapter on variables, okay? The different kinds of variables and how to measure them. So we'll say a lot more about that. But for right now, just understand it's a hypothesis, right? It's kind of an answer or kind of a guess to your question, or the question you derive from your observation. Next step, okay? Use the hypothesis to generate a testable prediction. Now, this is a step that's often left out when you hear the scientific method, let's say in a Psych 101 class or maybe another class. They usually just say, observation, hypothesis, and then they move on from there, to other things. But there's a third step, according to the scientific method that we're covering in this class, is that you have to generate a testable prediction. Your hypothesis is a general statement. The weather basically affects how people feel, okay? Now you have to make that hypothesis more specific, okay? You have to turn it into something that you can actually test. You have to turn it into a prediction. So you apply the hypothesis to something specific, observable, a real world situation. You have to be specific. So the weather can, make people feel more sad. That's your general hypothesis. Now make it more specific so you can test it. So you can be specific and say, well, if we decrease the light in let's say dormitories, right, where students live, right, that will make students, that will increase the rates of depression for those students, or that will make them feel more depressed, right? Notice how specific that is, right? We can decrease the light and it will increase depression for these students, right? So we can actually do that. We can make it darker in there, okay? Or we can make it brighter, and then we can ask students about how they feel. Another way to make it more specific so you can actually test it, right? Your general hypothesis, right? The weather is going to affect how people feel, okay? That's very general. Or your hypothesis can be, that people feel more sad when there's bad weather, right? But you can make that more specific. There should be less depression in cities with more sunshine than those with less. In other words, let's say places here like the Yango Valley should have lower rates of depression because it's very sunny here than, let's say, people who live in like Seattle, where, and I hear that it's always cloudy there, or very often cloudy, and it rains a lot. And there is actually research that says that, yeah, there are, higher rates of depression over there, okay? Imagine if you live in a place where it's always cold, always cloudy, even worse than Seattle. Seattle's actually not that bad, during the summer and other times of the year, okay? But let's say other places, that are, just always cold, always cloudy, you almost never get to see the sun. People tend to feel down after a while. We can actually test that specifically by looking at certain cities, and the amount of sunshine they get, and then looking at depression rates in those places. Note, you use your original hypothesis, right, the general statement, to come up with a testable prediction. Remember, your third step is that testable prediction. So you actually use deduction, you use logic, right? You use the rational method to reason from something general to something specific, okay? Did I mention that at the beginning we used, okay, maybe I'm getting ahead of myself, but okay, that's the third step. Okay, so the first step is observation. Second step is derive a hypothesis. And the third step would be prediction. You have to come up with a prediction. And that your prediction has to be specific, has to be testable. Okay, and here's an example of deductive reasoning, just in case you aren't clear on that. I know the letters are kind of small, but you can download this and make it bigger, okay? So your original hypothesis, right, is general, right? It's a general statement. The dark and dreary environment during the winter leads to depression. You can make that more specific, right? Use deduction. So when you go from general to specific, that's using deduction, okay? That's using logic, it's using deduction, okay? So prediction number one could be decreasing the light in college dormitories should increase depression for those students. That's more specific, okay? Or prediction number two, there should be higher rates of depression in Seattle that gets only 71 clear days and the rest are, basically cloudy and rainy. Then let's say Phoenix, that has a lot more sunny days. So prediction number two, there should be higher rates of depression in cities that get less sunshine than those that get more sunshine. That's deduction, right? Go from something general to specific. Let me explain deductive reasoning, deductive logic, in a more simple example that you've heard of, okay? You ever heard the expression, right? Here, I'll put it to you this way, okay? So there's the general statement, it's a duck. And then from there, you can derive specifics. It's a duck, therefore it quacks, it has feathers, it has a beak, it waddles, right? So you go from the general statement, it's a duck, to specific things that you should have or you could predict based on that general statement. Inductive reasoning, by the way, is the opposite, where you go from something specific to something general. Inductive reasoning would be, it waddles, it has a beak, it has feathers, it quacks. Those are your specifics, and therefore you logically deduce or logically use inductive reasoning to come up with a statement, it's a duck. Okay, so you go there from specifics to general. Okay, when you go from general to specific, that's deduction. Okay, just in case you're confused about that. The next step to the scientific method, the fourth step, you have to evaluate your prediction by making systematic planned observations. Let me put that more simply. The fourth step means that you actually have to test your prediction. To put it simply, you do a research study, you do a scientific study, you collect some data. So that's the fourth step, do some experiment, do some observation, do some survey, do some study to test your prediction, and you collect data. The goal is to provide a fair, unbiased test of the hypothesis by observing whether the prediction is correct, okay? So you do a type of study to see if your hypothesis is correct. You carefully observe what happens without subjective interpretation. You have to be objective. In other words, you have to let the data speak for itself. Note, the research study is an empirical test of the research hypothesis. We're using empiricism here, right? Relying on our senses to test that hypothesis. But there's more to it than that. There is often data, there's statistical analyses. So it's more than just empiricism. Okay, so that's the fourth step, to do some type of study. Okay, the fifth step, it gives me a number one there. It's not a number one. Okay, it's correct when you download it. Okay, at least last time I looked at it, but for some reason when I present it in the iPad, it changes things around a little bit. The fifth step is to then use those observations after you do that study, basically to determine whether your hypothesis is supported, or maybe it's been refuted, maybe there's no evidence for it, or maybe it's partly, supported, and you need to refine your hypothesis. You need to tweak it a little bit. So the fifth step, the last step, is actually to find out if the data, the evidence supports your hypothesis. Maybe it does, maybe it doesn't, or maybe it does so a little bit. So you might need to actually revise your hypothesis. You might need to tweak it. You might need to change it, Or you might need to discard it. You might need to get rid of it, say, ah, this is totally wrong. You know, we need to start from scratch. Or maybe it's supported and you just keep going from there and, you know, come up with other research. You might need to go back to step 2, okay, to come up with a new hypothesis if your hypothesis is not supported, if it's just completely wrong, okay? That's the 5th step. Some books will also throw in a 6th step, which I often do in my Psych 101 class or in other classes. There could be a 6th step, and that is when you actually present your findings to the scientific community. In other words, you try to publish your study. That is not in here. You only have to know these 5 steps, right? Observation, hypothesis, prediction, research. In other words, do some study, and then, you know, refine, refute. You basically, you know, check your original hypothesis to see if it's refined or refuted. I was trying to say that in less words. So the last step is basically, you know, to determine if your hypothesis is supported or not, or whether you need to refine it, you know, or get rid of it. Okay. This is what it looks like visually. Now, this is just to help you make sense of this. Okay. So we can start at the bottom with an observation. Okay. We saw something, right? And then we come up with, you know, a hypothesis, kind of an idea or an answer to, you know, to explain our observation, right? Then we come up with a prediction to test, you know, a prediction to test that, right? To test our hypothesis. And then we do planned observations. We do some kind of study. And that might lead to a new hypothesis. Maybe you find out that your hypothesis was not supported. So you come up with a new one. And then you have a new prediction. And then another study. And then maybe that could lead to a new hypothesis. You can see how basically science builds on itself. Whenever you observe something or you have a question, and then you do some research to try to find out what the answer is, what you'll often find is that, you know, you actually end up with more questions than you started with. Maybe you did find some answers, but other questions came up. And then now you should do more research to investigate those questions, come up with new hypotheses. Science always leads to more science. Research always leads to more research. Okay, science and knowledge builds on itself. We thought we knew something, right? And we tested it, and it turns out that we were partly right, partly wrong. So we need to do more research. Sometimes we find out that we're wrong and we need to try something else. That's how science works. It always builds on itself. It doesn't stop. Okay. Let's keep going here. So that was the scientific method. By the way, which you have to know very well. It's not hard, but you have to know that very well. One of the quizzes at the end of the semester asks you directly about the scientific method. And of course, so does the first exam. So you have to know it. If we had a face-to-face class, I would give you a short answer question on the scientific method. But online, the easiest way to do this is just with multiple choice. Okay, so that's what I'm doing, okay? Now, here's some other points to make about science in general. Okay, science is empirical, okay? The answers that we seek through science are obtained by making structured or systematic observations. So science does rely on the senses. It does rely on making observations, on testing things, whether you're testing, you know, sight, you know, sound, smell, whatever it is. It has to use the senses, okay? You have to see something, you have to test something. It uses the senses. It says the results will provide clear support for the hypothesis or will clearly refute the hypothesis. Okay, yeah, when you obtain your results, yeah, I mean, you could find that your hypothesis is supported or maybe it's not supported. But I should point out that that's technically not totally true, okay? The data could actually partly support the hypothesis and partly not. It could support it a little bit, okay? So that's not completely true, but science is empirical. It uses evidence, okay? It relies on the senses, and basically the senses allow us to basically determine if there's some evidence there. Science is also public and objective. I'll mention public first, okay? Public. In other words, when you do some scientific study, right, you have to share, you know, what you gained from, you know, with the public. Observations are made available for evaluation by others. When science is done, when research is done, you know, you write a research report and you try to publish it. And then what you try to publish it in some scientific journal, some academic journal. And then experts will review your work, will look it over, and might even ask you questions, and they'll determine whether your study is worthy of publication. So you try to publish it, you try to make it basically available to others. It doesn't do science any good if you do a study and you make this great discovery, or you find something that is really worth knowing, but you keep it to yourself like it's some secret that only you know, and therefore you don't want other people to find out. No, we need to make it public, right? So that others can test it as well, others can review it and see if you actually did it right, if there's actually some validity to that. They can try to replicate it, see if they can test it, do the same study themselves, slightly differently maybe, and basically replicate it. If several people find the same thing, then it's more likely to the case that there is something there, that there's some real evidence, as opposed to somebody who found something, determined something, and when other people test it, it doesn't work. So it might be that that study is flawed, or wasn't done right, or it's just not worth, probably not worth publishing. Okay, so you have to make it public, and that's how the knowledge base grows. Okay, think about all those early, basically scientists early on. Newton and Galileo and all that stuff. They all built on each other's work, and they were able to advance, mathematics or physics or whatever it is that they were studying, because people shared their work. They knew about each other's work, and they built upon their own knowledge. Somebody discovers something or basically figures something out, and then somebody else will come and look at that person's work and then add to that and make it grow. And that's how knowledge grows. You don't keep it to yourself. You share it with others. You try to publish it. And by the way, if you are a scientist, if you don't publish anything, then you're not going to have that great of a career. Okay, let's just put it that way. Okay, publications are important. There's a saying, right, that says publish or perish, right? If none of your work gets published, then eventually you're going to have to find another job. Okay, science should also be objective. Science should not be skewed by bias. You need to let the data speak for itself. Okay, you should not try to skew it for political reasons, or for any other reasons, because of your own bias, or because you want it to benefit you, or because you want to make sure, because you want to make it seem like you're correct, right? You can't admit maybe that your hypothesis was wrong or your idea was wrong. You need to let the data speak for itself. There's a lot of science out there, a lot of research, right? And I know that if there's some Trump supporters here, you probably won't like this, but there's data out there on climate change, okay? A bunch of data. Let the data speak for itself, right? You can't just attack the science and say that it's wrong, it's not true, just because it doesn't fit with your political beliefs. There's a lot of that happening. And it's not just on one side or the other, it's on both sides. That's how people are in general. When something doesn't support what they believe, their faith, their political beliefs, their assumptions, or whatever it is, they have a tendency to attack the science, right? And instead, maybe you should think, more rationally, more critically, right? And maybe read about it, see if there's other evidence, and, approach things more like a scientist, allow your mind to be open and to be changed, because very often we are wrong about things. We believe certain things because our parents told us that, or because of the church, or because of this or that, or because of politics. And we need to let the evidence speak for itself. I find it very distressing, by the way, that people attack the health professionals, the medical community, and they don't believe, the science. When there's decades of science that says something, and they're saying, no, those vaccines are causing autism. That's a bunch of bull, okay? The science does not support that, okay? Or, you need to let the experts, do their work and let the data speak, okay? If we do otherwise, if we attack it for political reasons, or because of our faith, or our, or personal beliefs, we are doing science a disservice, okay? But that's what a lot of people do. But when you're a scientist, when you learn how to do real research, you know better, right? And you don't just accept things either. You don't accept things blindly. We talked about those non-scientific methods of acquiring knowledge, but you do the research. You read the research, you do the research, right? And you approach things scientifically, okay? Science is supposed to be objective, not subjective. Subjective means that it's whatever you believe based on your personal opinion. You know, you need to let the data speak for itself. But there are plenty of uses out there where people use data to support their beliefs. They only take one scientific study that supports what they believe, when there's a whole bunch of others that say that it's not true, but they will look at that one study and say, look, see, I'm right. And then they ignore all the other ones. That is not the way to do things. And I'm sorry, to be kind of maybe a bit harsh about this, but I am a trained scientist. I am an experimental social psychologist. And it does upset me a little bit when people just attack the science just for personal beliefs or for political beliefs, or just because of what they believe based on their religion. I mean, it's okay to have your religion and things like that, but also keep an open mind. Know that in the past, people have been wrong, okay? The earth is not flat. People used to believe that in the past. We know better now, okay? So please, keep an open mind, especially when we're talking about scientists here, trained scientists who know what they're doing, okay? Medical professionals and all that stuff. All right, and this gets us to science versus pseudoscience, okay? The basis of scientific research. So evidence is gathered from careful, systematic, and objective observations, okay? So you do research, use the scientific method, right? And you do it right, you follow the steps, okay? Now, there's something known as pseudoscience, which is fake science. There's a lot of pseudoscience out there. There are things that people believe, ideas that are presented that people believe that somehow are true, and are presented in a scientific way when it's not scientific at all. It's fake science. And this pseudoscience lacks some key ingredient, some key component essential to scientific research. It lacks something, some part of the scientific method. Some examples here: aromatherapy, and I can give you others, but aromatherapy, right? That these scents that you can buy, whether it's incense or whatever it is, all these different things that somehow that can heal you. It will definitely affect your mood. There is some evidence to that, but the fact that it can heal you, okay, or cure cancer or things like that, I mean, come on, right? Going too far there, right? Now, there does seem to be some science there, where people say, oh yeah, we tested this and, people feel better afterward, or, it is presented as science, but it's often not done right, or it's just, they ignore evidence that contradicts, what they're saying. Okay, that's not a good example. A better example is astrology. Okay, astrology. Come on, your horoscope. There's like what, 12 of them or something like that? Really? How many people are there? Is it possible that the movement of the stars have something to do with what's going to happen to you? But they say, look, we measure the position of Venus over here and Saturn, and that means that you're going to be having good luck on, in the coming days. It sounds scientific, right? Measurements, and they're, kind of associating things, but it's a bunch of bull, okay? It is not science, okay? Or intelligent design. Intelligent design is basically the biblical approach to, to basically, to try to explain what we have, why we have the animals that we have and the plants and all that stuff. It's a basically contrary idea to evolution. Evolution is a theory, has a lot of evidence behind it. It's been tested in many different things. Intelligent design says, no, we have a creator. He made everything and made everything intelligently. It's not science, guys. I'm not telling you shouldn't believe in God or shouldn't go to church. Just to point something out here, just so you know where I'm coming from. I believe in God, okay? I am a believer, okay? But I also know the limitations of religion, okay? And the limitations of things, okay? But I am a believer for personal reasons, because of faith and things like that. But this is not science, okay? And religion shouldn't try to pretend that it's science. It's a totally different approach to acquiring knowledge. It's the method of authority, right? God said this and that, and then your pastor or your priest interprets it, and then you believe them. That's one way you could know things. Some of those things are probably wrong because, no one knows everything. And they think they know what God said or whatever it is. I mean, there's a lot of assumptions there, but science works differently, okay? And it's not, intelligent design is not even a theory. It doesn't even qualify as a theory. It's just not science, okay? There's other examples. There are all kinds of weird things out there that a lot of people believe. Like, there's people who believe that if you wear like orange glasses, that it'll help you with digestion. It'll help you, go to the bathroom more regularly, or that, you know, if you, you know, or that if you just listen to, you know, certain sounds that it'll make your kids smarter or something like that. I mean, there's all kinds of fake science out there, okay? You need to look at the real research, okay, and learn how to do research. And you guys are gonna have that advantage by taking this class. You'll know what real research looks like. And you'll be, and hopefully, if you go on to graduate school and you get really good at this, you'll even be good enough so that, you know, you basically will be able to look at research that is very well done and still be able to point out what is wrong with it. Okay, when you are that good, right? When you really know about research, because you know what? No study is perfect. No research is perfect. We're trying to approximate something. We're trying to collect evidence. We never prove anything. We just find evidence. But these things, they're not science. And there's a whole bunch of other examples of pseudoscience, of fake science out there. And for some reason, I can't think of so many others because I guess I've gotten a little bit emotional. I get a little bit frustrated when I see these kinds of things and stuff like that. I guess I take it a little bit personal as a trained scientist myself when I see this and I see so many people falling prey to this stuff, okay? When there's real science out there that they should believe, okay? Or that they should look up, especially in our age of the, you know, where we're always online on the internet, everything's readily available. You can really do, I mean, do the research, right? And don't just do some Google search. Go and I'll show you where you can actually find real studies. You should know actually already. You have sources available to your library. Okay, the research process, you know what? I think, yeah, we're almost done here and then I'll open up to questions, but the research process, I am not actually going to go into the full research process, but we will go through the research process step by step and I'll show you how to design your survey, how to analyze your data, all that stuff. But here, this is just a point here. There's different kinds of research, okay? There's qualitative research and there's quantitative research, okay? Quantitative research actually is the kind of research that produces statistical data. It produces numbers, okay? It produces things like that, that you have to run statistical tests, tests of significance, things like that, correlations, t-tests. That's the kind of research we're more used to hearing about. And that's the kind of research I want you guys to do, by the way. But there's also qualitative research, which is based on just making observations where all they do is summarize and interpret something in some kind of written report. There are studies, for instance, where they, you know, maybe they'll just do a survey about depression and they'll ask people about their symptoms. And then they write up the report. You know, so according to this, you know, study, you know, depressed people tend to, I mean, people who are depressed tend to have, tend to feel sad. They tend to have a, you know, decreased appetite, decreased sex drive, trouble sleeping. And they just basically mention things like that. There's no numbers presented, but that is still a research that was done, although it's qualitative. All they're doing is saying things without the numbers, without running any tests. They're just reporting what they found based on an observation or based on a survey. They don't do any statistical tests. You guys are going to do the type of research that actually requires numbers, by the way. Here's the thing. I think I know what happened here. I actually shortened this just so we can have a little bit more time. Now here, the steps in the research process, I am not going to go over that. I actually cut this out last night and I uploaded. I thought I uploaded the new PowerPoint, okay? But that stuff is still in there. But we will go through this, the steps in the research process, as we go through the semester, okay? And we will start at step 1 and all that stuff. This is just the introductory chapter, okay? So we will stop there. I am going to stop recording.